Proving the stability of navigation cycles. It is a common work with Auguste Bourgois, Amine Chabouni, and Andreas Rowe. In this talk, I will consider the problem of navigation cycles in the context of underwater robotics and show how interval method can be used to prove the stability of cycles. So we have to understand that as represented by this picture, we have a torpedo like this one that can move left and right and go straight most of the time. And inside we have a gyroscope or proprioceptive sensor, so that the torpedo knows something like its speed and its heading, but the only interaction with the environment is via an echo sounder, and it can measure the altitude of the vehicle. So by altitude I mean the distance between the robot and the seafloor. Okay, so how we can move without getting lost? The only possibility we know is the cycles that are used by animals like turtles, marine turtles, that are able to move far in the ocean and come back. So I illustrate by the cycle, the notion of stability cycle, by this picture. I consider a robot here, like this, which is able to move inside a pool, represented by the blue rectangle. So it moves with respect to the heading psi1, like this, and it will go straight until it reaches one of the wall, like this. And then once it reaches one of the wall, it will change of strategy and will follow another heading psi2, like this. And then a new wall, it will follow the heading psi3, like this. Another wall, psi4. And after, it will come back to psi1 again. And we understand that if the robot follows the strategy, then it will easily converge to the red rectangle. Here we see an illustration of what is a stable cycle. So we have a robot with no GPS, and the only way he has to feel the environment is to feel the collision. It's done at Ensta-Bretagne in Brest. We have the robot here with a echo sounder for the distance, and it is able to measure the distance here. And a way to perform a cycle is to rebound as soon as we have reached a given isobat. So for instance, here if I take 10-meter dip, so minus, when the robot will be here, it will measure with the consider 10 meter and it will change its heading. So how can we do a cycle like this? So assume that here is a 10 meters isobat, so a level curve, and assume that the robot is starting here. So it will follow a heading due to the uncertainty, so this heading for instance, and due to the uncertainty, the cone is increasing like this, and it will stop, change the direction as soon as it enters in the new isobat, so here minus 10 meter. It will change the heading and go to this heading, like this. And again, the uncertainty increases. And after, as soon as it reaches the isobat, it will change the heading, going to this one, and so on. Always the uncertainty increase, but we can understand that if it follows this, it will perform a stable cycle and will never be lost. So to prove that we have a cycle, we first need a model for the robot. And the model we consider is a Dubin's car, which is described by this differential equation. So let me recall that here I have the position of the robot x1, x2. The robot is represented like this, x1 x2, the position, and the heading is x3. And we can control the heading by U. So we propose a proportional controller like this one. So it is the desired heading. Here it is some kind of distance, the error between the actual heading and the heading we want. And we take the sign to remove the problem of 2 pi modulo 2 pi, and we get a classical proportional controller. So this one should enter inside this one, and the control system will have as a new input the desired heading. For the controller, I propose the following strategy. So we have 3 states, 3 discrete states, so Q equals 0, 1, and 2. And we have a counter C, a timer C, and for instance, we switch to Q equals 0 to Q equal 1 as soon as the counter is greater than 5. And of course, at each, when he moves, the counter is initialized to 0. We have here, when we are in a state, we have some desired heading, which can be 0, p divided by 2, or 4, like this. And we switch from one state to another with a counter, or when some conditions are satisfied. And now we have equation, and what we want to show in this talk is how we can prove the stability of such a cycle, which can be considered as an hybrid system. So for the simulation, I propose to run the simulation, and you can do it by yourself using this link. The robot starts here with Q equal to 0, so it follows the heading going to the right. Then after 5 seconds, it goes up, and here it rebounds on the parabola and turns left to follow the heading C3. Then as soon as it reaches this line, it changed like this. Here we have one cycle with Q equals 0, Q equal 1 red, Q equal 2 green. We see the parabola and the line. Then we have many cycles here, and the car is represented here by points, and we can guess here the limit cycle. So how can we prove the stability of the cycle? The main tool for this is a poincare map. Okay, so what is a poincare map? We have a state equation, x dot equal f of x, so the derivative with respect to time. And we have a section, so it means it's a function from Rn to which x belongs to R, so it means that it is a scalar equation. And a transversality, which tells us that the dynamics of the system will not generate solutions that are tangent to the surface. So most of the time the transversality condition is satisfied. So we'll assume this. Then the surface is inverse image by G of 0. So what is poincare map? It is a function which takes a point A in the surface and associate another point P of A, P like poincare. So it means that when the trajectory is initialized at A, the solution will cross again the surface at P of A. So I represent here an illustration in 3 dimensions. So I have a trajectory here. So I assume that my system is at state A, then it will leave the surface and come back to the surface at P of A. So it is an illustration of the poincare map associated to the state equation and to the surface S. Then I can see the dynamic of the system as a discrete system. So here I have represented the surface like a plane, R2. I have here my point A is now here, and P of A is now here. So I will generate a sequence A, P of A, P of A, and so on. and probably I will converge to A bar. If it is the case, then it means that I have reached the limit cycle. So it's a main tool for proving the stability. So what we call the poincare first sequence map is this discrete time system, and we can prove easily the stability of this by computing the Jacobian of P at equilibrium point A bar. With hybrid systems, the principle is similar, but we have several dynamics. So we have, depending on the heading we are following. So assume that I have M dynamics, for instance, M heading in my situation. So M equal to 3 in the examples I have given before. I have different bounding surfaces. I assume that I have the transversality condition, and the automaton tells me as soon as I have reached the ith surface, then I switch to the next dynamics, so to the next heading given by this formula. So I can see here a representation. I have a point A, then I follow the dynamic, then I reach another point, I will follow another dynamic, and then I will come back. Let me consider again my cycle here. I have my initial condition, which is here, and in my state space it corresponds to a point of in the surface S2 equal minus 2. So recall that I have in my map x1, x2 only, but due to the heading I also have to consider x3, of course. So assume I take one situation like this. Blue situation corresponds to 1 point. After one cycle I will reach another point like this one, and slowly I will converge to this point. But it's not guaranteed, it's just an approximation of A bar of the limit point. Now, if I need to estimate the Jacobian matrix of this at point A bar, with a numerical method, I am able to estimate the Jacobian of the Poincare surface, and I obtain in my situation a 3-3 matrix here, but only the first component is associated to my surface, so x1 equal minus 2, so it's not interesting for the stability, but only the two last components have to be studied for the stability. So I extract this matrix, which is given here. Again, it is an approximation. It's not an interval which encloses all solution. I compute the eigenvalues, and if the eigenvalues are inside the unit cycle, since I have a discrete time system, I can conclude without any guarantee that the limit cycle is stable. So what I want to do now is to use interval method to have a proof of this. Validated approach has been presented by the following papers that are given in the references. They use some ordinary differential equation solvers using interval methods. So here it will be CAPD. And we have plenty of numerical examples which illustrate the method given in the thesis of Auguste Bourgois. For now, we'll discuss about the validated stability just to give an idea how this can be done. I have to introduce the tool, I will consider a state equation x dot equal f of x. I will consider the flow with initial vector x0 at time t, and phi of x0t corresponds to the state, to the solution of my system, to the state of my system at time t if it is initialized at point x0. Now for the stability, I need to consider the derivative of phi with respect to x0, and this quantity, which is a Jacobian matrix, I will call it A. Okay, and I have this Jacobian matrix, this matrix A, which depends on t, obeys a differential state equation which is given here. So here I will have analytical expression. Since I have an analytical expression for f, I have an analytical expression for the Jacobian matrix of f with respect to x. And of course, due to the property of the flow, at time t equals 0, A is equal to the identity matrix. So just to give an illustration for non-specialists, I consider here an example with a van der Pol system. So it is a state equation of the form x dot equal f of x. And my matrix A, which corresponds to the derivative of the solution with respect to the initial state, satisfy this differential equation. Okay, so here it is a Jacobian matrix with a derivative of f with respect to x. It is a 2-2 matrix. In the case of the van der Pol system, of course. And the initialization for J is the identity. So how can I integrate all this? I have to perform a scalar decomposition of this equation, and I obtain something like this. Okay. So here I have the coefficient, the derivative of the coefficient of the matrix A. Here is the derivative of the state, and on the right hand side I have only some x1, x2, and the entries of the matrix A. So I have here a classical state equation. If I integrate this equation in a guaranteed way using an interval solver, then I will be able to enclose not only the state but also the entries of the Jacobian of the poincare map. Here is my Cartesian view of my surface, which is here, S, and corresponds in my example to x2 equal -1. So I consider here a box, and inside my three-dimensional space x1, x2, x3, the two-dimensional space here, two-dimensional box, is enclosed into a three-dimensional box here. Okay. Then, using the interval ODO solver, I am able to integrate along a trajectory to get a three-dimensional tube. Okay. And this tube will cross the surface. So if I draw J of x on this tube, so I will obtain a slide like this. I will obtain a scalar tube, G of x, and this tube will be equal 0, will contain 0 at the beginning, and then when I will integrate, it will not contain 0 anymore, and again it will cross 0 like this. So since I am able to differentiate when J dot is negative and when G dot is positive. So remember that G dot of x is equal to the derivative of x to the Jacobian matrix with respect to x times x dot, and x dot is f of x. So it means that I have analytical expression of G dot, so I know when G dot is positive or negative. So here, sorry, it represents something like positive, and here negative. Okay, so now from this I am able to extract an interval here which tells me when the time at which I will cross again the Poincare surface. From this interval I will consider all cubes that associated to each slide that are represented here in blue. Then I will enclose all of them inside a cube, all the blue one, and I will obtain here the image. Okay. So most of the time, due to the stability, the green one will be smaller than the red one. So if I continue like this, I will converge like this probably to a point, but at least not only I am able to enclose X, but due to the variational expression, to the variational state equation, I will be able to enclose also the Jacobian matrix. Here we have another illustration of the underwater robot performing a cycle in the ocean near the harbor.